So this is the machine that does the job.
Yes.
What is actually going on here?
So what you see is a machine that takes crushed rock, we mix it with water, and then we put it into this reactor, and we mix it with CO2. That CO2 then chemically bonds with the crushed rock and then turns into a product that can be used to replace cement.
Like a cooker, almost, maybe?
Absolutely. You can kind of describe it as more like a pressure cooker. Like it operates at higher temperature and high pressure. This is a naturally occurring reaction, but we do it instead of over 1 million years, what normally takes the planet to do, we can do that within an hour.
Unlocking this natural process into something that can be done at speed and scale is the goal for researchers here. The main ingredient in their process is a mineral called olivine.
The way traditional cement is made is that you take this mine product and you add a lot of heat to it. You warm this up to 1400 degrees C, and in the process, what you end up with is cement. But in that process, you lose half of the mass. You've generated a lot of CO2. For every ton of cement that you produce about 900 kilograms of CO2. What our process does is it takes a different mineral, but the same amount, but instead of emitting CO2, what we do is we take the CO2 and we bond it into this mineral, and what you end up with is a product that actually, you end up with more of it than what you started off with.
With the CO2 locked away, the product can now be deployed by blending it with existing ingredients. That reduces the cement needed by 25%. In Rotterdam, there are already projects starting to use pebble in the construction of precast panels.
There must be a lot of nervousness in industry about using a new material. Concrete has been used for hundreds of years and has, stood up to testing in the real world. How can you convince people that this is actually going to work?
Yeah, so first of all, the nervousness is there for a good reason. Anything you build with concrete cannot break down. It's the bridges we drive on, it's the buildings we live in. We need to go through the regular certification routes, as any material needs to go through for good reasons. You try to expose it to accelerated stresses and cycles that it would experience anyway. So where there you get the temperature cycling, you get different kinds of humidity cycling tests, and so on and so forth, which you may be running for 1 or 2 years, or sometimes even longer. At the same time, what you want to do is you start with the lowest risk applications within concrete. We're not going to be building the structural pillars of a high-rise as the first thing. We're going to be going into non-structural concrete, which is what we're doing right now, at first, so that we can reduce the risk, we can actually deploy the material into the real world at meaningful scales and see how it behaves.
As the world keeps building, there is a race on to develop more environmentally friendly materials, and that means lots of startups are crowding into this space. Who comes out on top will be those who can prove they can make this cost-effective at scale.
We need to solve this problem quickly, and that drives all of us. So the speed is definitely both exciting, but also a little bit scary, because none of us have done it at this pace before.